We're doing a video here on reducing circuits and solving them all out. We've got kind of a complicated looking situation here, but I'm going to show you how to reduce it and make it simpler. You're unlikely to get one quite this complicated, but the nice thing about this is that as we reduce, it'll get to the simpler versions and show you how to do the simpler ones. As you see right here, we have a cell or a battery, our voltage source here, and then we have a bunch of resistors all along here. All of those things. One of the things that I probably should make mention of is that these voltage sources, when it's a source of voltage, we don't call it a voltage, we call it what's called an EMF, an electromotive force. And we can talk more about that later, but sometimes you'll hear these referred to as an EMF. And basically it's the voltage you get from a battery or a cell. It's a provided voltage. We'll have voltage drops, which are as these resistors take away voltage, they reduce it. And then we have voltage gains, which are given to us by these cells that are called EMFs. Okay, EMF, it stands for electromotive force. Not a good name because it's not actually a force, but anyway, we need to start off by going through and reducing this. So if you remember from last time, if we have any resistors in series, then we reduce them just by adding them up. And series are any resistors where any electricity that goes through one, any single electron that goes through one must go through the other. So we're going to start by just ignoring the direction of the voltage here, and we're going to look and see if we see anything. So we can compare this R and this R, and you want to check forward and backwards. Like if I flip this battery around, it'd still work. So if I have an electron come through R, it can totally skip and go this way and never go through this R. And the same thing if I go the other way, if an electron comes through here, it may have to go through R and go the other way. It can come up here. If it's trying to get to the end of the battery, it has to go through R. But one way forward, it had to go through one of them. One way, the other way, it could skip the other. So that's not either series or parallel. But if I look at these two, any electron that goes through this one must also go through this one. That says series. And if I go backwards, an electron coming through this other one goes through it, and it can't go anywhere else. It has to go through that one. There's no other path. So both forward and backwards, this one says series. So these two, I'm going to put a circle around them, they're in series. All right, these are in series. Okay, I didn't write that very dark. Series. Okay? Yes. Okay, series. And then look here. What about these two here? Look, if I'm an electron, I come through this resistor, there's nowhere else for me to go. I'm going to eventually have to go through this second resistor in order to go back to the beginning. And the same thing, forward and backwards you check. Go through this resistor, and then there's nowhere I can go. I must go through that resistor. So these two are actually in series as well. We're going to circle everything in series in yellow. And then look at these five over here, 1, 2, 3, 4, 5. If I go through this first one, I have to go through the second one. If I go through the second one, I have to go through the third one. If I go through the third one, I have to go through the fourth one. And then I have to go through the fifth one. There's no other alternate path. And then go backwards with it. If I go through this one, I have to go through that one, and I have to go through that one, and I have to go through that one, and I have to go through that one. So this grouping here, these five, are all in series, which means we can start reducing. Since they're each all the same R, I'm going to leave that variable on there. And what we can do is reduce our circuit by redrawing it. So it won't be as neat as my first picture, but here's our battery. Okay. And we're coming over here. This guy, he stays there. We didn't do anything with him. He's still just R. And then we come over here. We didn't do anything with this guy right here, so that one stays R. Okay, we come across. These two were in series, so we can add them up. So whatever they are, we can replace this R and this R with a 2R. They're the same, which would be 20 ohms. We can come over here, and now these two we can replace with a single resistor, and there's nothing that says we have to keep our wire curvy, so we can just put it in a straight line, put our resistor in, and we've got, now that's supposed to be connected, we've got a 2R here as well. And then over here we had those 5. We're going to reduce them down, adding them all up, put that resistor there. We could have put the resistor up here or down here, anywhere, as long as we don't cross a junction or cross any other components. So as long as we don't cross, these are called nodes, the places where the little wires meet. As long as we don't cross any of those, we can put it really anywhere. 5R, because there's 5 of them, so this would be 50 ohms. And there we go, we've done our first reduction. So now let's look and see for series again. Do we have anything in series? Well, again with these two, if I go through this one, I have to go through the second one. If I go that way, but if I go through this one, I can go over this way and go all the way around and never go through R, so I can skip it. So these two, definitely not in series. And then check the other way. Nope. If I go through one, I have to go through the other. That's definitely, it looks like series one way, and it looks like parallel the other way. So that one is not either. Same thing for these two. They're in the same kind of configuration of these two, and those two are. But look at these two here. Go ahead and, oops, I don't want to circle them in yellow. Let's circle them in green. Look at these two here. These two are in parallel. And I'm going to tell this because if I come along and I go through this resistor, I can come out here and I can get all the way to the beginning without ever going through that guy. And then go the other way. If I come through this resistor the opposite direction, I can totally skip this 5R1 again. So these two, same thing here. If I go through the 5R1, I can totally skip the 2R to get to the beginning. If I go through this way, I can totally skip the 2R1 to get all the way back to the battery and never actually have anything to do with it. So now we're going to get a little trickier. Now we have to add up the reciprocals. So here these were series, so we added the we just added them, but here they're in parallel. So now we have to add the reciprocals. So this becomes, oops, what happened there? This becomes 1 over our R equivalent is equal to 1 over 2R plus 1 over 5R. And a common denominator for those would be 10R, so 10R in the denominator. And so that'd be 5 plus, so I have to multiply this one by 5 on the top and 5 on the bottom, and this one by 2 on the top and 2 of them, so 5 plus 2. And so our equivalent is 10R over 7. There we go. And so we can redraw this one now. I'm going to have to scoot down. I'm running out of room. Redraw this one now. Do our next step. Here's our battery. Coming on over here. We've got a resistor right here. This resistor here. R. We've got this resistor here that's 2R. And now we're replacing this with just one single resistor. That right there. And there you go. This one is 10R over 7. So that's what, 100 ohms over 7 is what that's going to be, because R again is 10 ohms, but we're not worried about that just yet. We'll do that. We'll start worrying about what it is when we start doing Ohm's law. So now we've got this, and see how we're getting a simpler and simpler picture? And so now we need to look at this and we need to decide, is there anything in series or in parallel? So let's look at this. Well, if I come through these two, we already decided a long time ago, nothing's changed as far as they're concerned. We can still come through this guy and totally skip the other one. So they're not series, and if we come the other way, I could have to go through it. So it looks like series one way and parallel the other, so they're nothing. But look at these two. If an electron goes through this one, it has to go through this one in order to complete its path and get to the beginning. And if we go the other way, an electron goes through there, it has to go through there in order to get to the beginning. So these two are series. Okay, so these two are in series, which means we just add them up. So we add them up. R equivalent is equal to 2R plus 10R over 7, which means this is what? 14R plus 10R over 7, right? Because this could be a 14 over 7. And so we get 24R over 7. And that's our equivalent resistance. And so now we come down again and we redraw our picture with our new one. And so we've got our battery here, but thankfully our picture is getting simpler. Okay, come through, we've got this R, and now we're just a few steps away. We only have a few more pictures to draw. And now we've replaced those two with this one, and we've got 24R over 7. We've got R, and we've got R. And now we look, nothing has changed for these two. Go forward. I can skip the other one totally and get all the way around. If I go this way and go through that one, then I have to go through that one. So it looks like series, looks like parallel, depends which way you go. So it's neither. But look at these two. What do they look like? Hopefully you're saying they look like they are in parallel, because they are. These two are in parallel. All right? They're in parallel. And so if they're in parallel, that means that I can go through this one and forward or backwards and never go through the other one. And I can go through this one and never go through that one, forward and backwards. Okay? So these two are in parallel, which means we add up the reciprocals. So 1 over R equivalent equals 1 over R plus 7 over 24R. So this is a 24 and a 24, and that gives us then 24R, skip a little bit of the math, over 31 is R equivalent. So I added them together and took the reciprocal, right? It'd be 31 over 24, and I took the reciprocal. So our equivalent resistance for that is, redraw it again. I know it's a lot of redrawing, but that's okay. We've got this resistor here that we just reduced is now 24R over 31, and this one's just R. And these two, the only ones we have left, they are definitely in series. If I go forward, I have to go through that one. If I go the other way, if I go through that one, I have to go through. So now I have to go through both of them, which makes them be in series. So these are in series. Okay? And when they're in series, we just add them up. R equivalent is equal to R plus 24R over 31. So this is 31 and a 31. So what does that give us? 31 plus 24 is 55R over 31. And that's our equivalent voltage, or I'm sorry, our equivalent resistance there. And we can go ahead and just draw ourselves one last picture here. One last picture, move down a little bit, and we'll have a picture with only one single resistor and one single cell here. And this is 55R over 31. Okay? And so essentially, if you go back to that crazy picture we had up here, this guy, that picture right there, we could replace all of these whole bunches of resistors, right? All of these 10 ohm resistors with this one single 55R over 31 resistor. This is 6 volts. So what did we have? We had our voltage was 6 volts, and each resistor was 10 ohms. So now we can start plugging some numbers in and see what values we can get. So this one's going to equal out for us of 55 times 10 divided by 31. It's going to be about 17.7. I'm going to just kind of do these approximately. I'm not going to try and maybe carry these through all the way. But anyway, I've got this. And so now that was our step one. Reduce all the way down to one resistor. Okay, if you remember the rules we did. That was reduced down to one R equivalent. I've done that. This is my one equivalent resistor. And what I'm going to go ahead and do then is do to step 2, which is apply Ohm's law. So I'm going to go back and apply these Ohm's laws using red. So this is step 2 now. That was all step 1, reduce to one single resistor, apply Ohm's law. So we've got V equals IR. We want to solve, we have R and we have V. This 6 volts is what's going to be applied there, so 6 volts. And so I need to solve for current because that's what I don't know. That's V over R. That's 6 volts divided by 17.7 ohms. And so if I do 6 divided by that, I get current of 0.34 amps. So I can write here on this resistor 0.34 amps. Okay? So that's step 2. Reduce it, apply Ohm's law. We've got 6 volts, 17.7 amps, 17.7 ohms, 0.34 amps. That's all that's going through here. So this is the total current coming out of our battery and through all the resistors somehow combined. So now, step 3, step back. So we're going to step back to this one. If you step back to series, then the thing that is the same for series is current. That means when we step back, this guy will have 0.34 amps. So we're going to step back, we're going to carry the current. 0.34 amps. Okay? We know what the resistances are. We already found them. This is equal to 24. So that's 240 divided by 31. That's 7.74 ohms. So we know the resistor here. We know how much current is going through each one. This is 10 ohms. And so what we can do now is step back, carry current because it's series, and apply Ohm's law. But we need to apply Ohm's law for both of them. So for this first one here, we have V equals IR. We want to find the voltage drop because we know current and we know resistance. So it's simply that 7.7, right, times that 0.34, and we should get about 2.62 volts. And so we can write that here, 2.62 volts. That's our voltage drop. That's our current. This is how much voltage is dropping here. This is how much current is flowing through, and that's our total resistance. And so now we can apply Ohm's law to this resistor as well. V equals IR. We're trying to do the same thing, but this time I is again 0.34 amps. But now R is just 10 ohms. And so we plug those in and we should get 3.4, about 3.4 volts. And if you look at this, 3.4 plus 2.6, what does that give you? 6. 6. All right, so that's going to be one of our laws later on we'll have to worry about. Like I said, when you put these in series, I believe I referred to it in the last video, I said it was a voltage divider. They're in series, these two here, so it split our voltage. 2.6, 3.4. Really, it's not 3.4 volts. It's really like 3.38182. There's a lot more decimals on my calculator here, but it's about 3.4, and this is about 2.62. And if you add up the more exact values in the calculator, they'll give you exactly 6. All right, so this is 3.4 volts, and those are our numbers for that one. So that's step 4, or step 3, and then step 4 is to go back and repeat these steps. So we stepped back, we applied Ohm's law, now we're stepping back again. So let's step back this time. This time, this guy's not changing, so we don't have to do anything. He's still 10 ohms, he's still 0.34 amps, and I'm not going to write this every time, and 3.4 volts, because we didn't do anything to him at that point. But this guy we split into parallel. And if we split into parallel, the current isn't the same because the current's going to split. Some's going to go through here, some's going to go through here. It's going to split, it's not going to be the same. So we carry back the voltage. That's this 2.62. So we can say this has a 2.62 volt drop and this has a 2.62 volt drop. Okay? And then we can go and apply Ohm's law. So for this guy, we know that it's V equals IR. We have the resistance, we have the voltage, we just need current, so I is V over R, and V is 2.62 volts, and R is 10 ohms in this case, and so this becomes 0.26 amps, and so this is 0.26 amps. So that one's pretty easy. And now we apply Ohm's law to this one. And again, we want to find current. I equals V over R. The voltage is 2.62 volts. The resistance is 240, what is that? 240, it turns out to be 34. Let me get my old eraser here. I'll write it exactly. 24 times 10 over 7, right? It's a 10 ohm resistor. Should give us 34.3 ohms. And so 2.62, that number, divided by the 34, gives us about 0.076 amps. 0.076 amps. And if you look at this, we had a total of 0.34 amps, and if you add 0.26 and 0.08, about rounding them off, you get the 0.34 back. So what they're saying is when we split this into series, the current split between them. Not evenly, but it's still the same total amount. That's just conservation of charge. However much current was flowing through this one would have to split between those two. And now we go and we step back. Now that's a lot of this. This is stepping back into series. We didn't do anything to this one. It's just going to stay. It's just going to stay. I'm not going to bother rewriting it. But now we're stepping back into series. With series, we carry current. So this is 0.076 amps, and this is 0.076 amps. And we apply Ohm's law. All right, we have current, we have resistance, so we're finding the voltage drop, V equals, and this first one is 20 ohms, the 2 times 10 times 0.076 amps. Sorry, I'm running out of room there. And that gives us, on this one, 1.5 volts. So 1.5 voltage drop there. And for the other one, it's, what is that? 100 divided by 7. How many ohms is that? 14.3. 14.3 ohms. 14.3 ohms, that's supposed to be in ohms, times the 0.076 amps. And so if we take that number and we multiply it by that number, multiply those together, we should get 1.09 volts. And if you add this, what do you get? The we should get a total. If we had all our decimal places out here, we would get then this 2.62. Really, I think it was a 61 or something like that. But we'd get this back. Okay? If you had these extra decimals out here, we'd get this 2.6 volts back because the voltage drops across each one. It's a voltage divider, and we get that. So 1.09 volts. I have it a little more exactly on my calculator. And then we step back. And now we're stepping back, and we're going from series to parallel, so we carry voltage. That means this is 1.09 volts. We're stepping this guy back, right? This carries up unchanged. This carries up unchanged. This carries up unchanged. We didn't do anything. This guy we're splitting 1.09 volts. I didn't leave myself very much room, but try and squeeze it in over here. And so we have V equals IR, so now apply Ohm's law. We've got that we want to find I, because that's what we're missing, so it's V over R. So this is 1.09 volts over 20 ohms. So that gives us 0.055 amps about. For the other one, so this is 0.055 amps. For the other one, we've got the 1.09 volts over the resistance. This is 50, right? The 1.09 divided by 50 this time, because this is 50 ohms over 50 ohms, gives us the 0.022 amps. And if we add these up, we should get back our 0.076. And you can see that we get about this. This is actually 0.021, and this is 0.0545. So if you have these extra decimals, these two would add up and give you that right there, because that's that amount of current splitting between these two. So this is 0.022 amps. There we go. And now we take one last step back. This guy just carries up. This guy just carries up. This guy now splits, right? So we have to go back down and look at what he was. What did he have? What did we get for him? 0.76 amps. So he's splitting now into series, which means we carry the current. So this is 0.076 amps and 0.076 amps. And then this one splits series, so we carry back the current, 0.055 amps, 0.055 amps goes with that one. And then these are all series, so we carry this back, 0.022 amps, 0.022 amps, 0.022 amps, 0.022 amps, 0.022 amps. And we apply Ohm's law. Thankfully, we only have to do it these one last time. These all went to series. So these are the same. They're the same resistance and same current, same resistance, same current, which means we can just apply Ohm's law once. So we need to find V. So V equals I, 0.076 amps, times R, which is 10 ohms. So this should be about 0.76 volts. So 0.76 volts. And then this one will also be 0.76 volts. I'm running out of room, so I'll write it up there. Now we come down to this guy. V equals IR. This is 0.055 amps times R, again, 10 ohms. 10 ohms. This is 0.55 volts. So 0.55 volts, 0.55 volts, volts. And then if you look at these, they're all the same, but it's the same pattern, right? V equals 0.022 amps times 10 ohms. They're all just R with that 10 ohms, so 0.22 volts. And so 0.22 volts, 0.22 volts, 0.22 volts, 0.22 volts, and 0.22 volts. And again, you can see 0.55 volts plus 0.55 volts should give us back our 1.09, so about 1.1, which is what we get. Again, these are rounded. And then here, 0.76 should give us back our 1.5, which we have right there. There we go, just about, again, rounding errors. And 0.22, 0.22, 0.22, 0.22, 0.22 should all add up to give us this 1.09, which is about what it is, because 0.2 times 5 is 1, and that's what we have there. All right, so we have fully solved this. I know it's an ugly mess, and I probably should go back down here and grab the results of those two, of like this one and write them up there, but there it is again. You can write them up there. But we fully solved this. So if you've got a problem that asked you, what's the current through this resistor, you could stop after you got it. You wouldn't have to keep going and doing every single one like this. But I wanted to go ahead and just solve the whole thing for you. But usually they'll say you something like, what's the current through this resistor? And you start reducing it down and finding it. And also you're probably likely just to get one that's a little simpler than this, and you have to go through and do it. Okay? I think that's pretty much everything for this one. It's just a nice quick little example. I guess not super quick, a little bit long of an example. In the next video, I'm going to show you a sample of one of these. You should practice some of these and get good at telling series from parallel. I'll show you a sample of one of these that you cannot reduce. There's nothing in series and there's nothing in parallel, so it can't be reduced, which means we can't actually reduce it to solve it. And we're going to have to come up with some other rules to use to solve it. And in fact, I guess we don't have to come up with the rules. Somebody else came up with them. They're called Kirchhoff's laws. And therefore, solving circuits like this, you can use it to solve these circuits here too. But usually it's a little more difficult, and you want to use it only when you can't reduce them. Okay? I think that's just about going to do it then.